3-4B. Hi, good morning. Come on in. We just started our lesson on rates of change. All right, rates of change. I have 2 parts today. We're going to talk about the change in volume or area, and then we're going to do some velocity graphs. Have you guys done velocity graphs before? Yeah. In physics? They're hard, huh? No?
So velocity.
Then to acceleration?
Yes. Yeah. No, you'll be okay. Yeah. Okay, 2 parts. Here we go. We're going to do some volume and area problems. And they're going to be changing. The volume's going to change, the area's going to change, and with calculus and derivatives, it's going to make our lives so much more simpler. All right, so number 1, here we go. It says to first write the area of a circle as a function of its radius. So what is the area of a circle? Pi r squared. Perfect. Area equals pi r squared. Okay, so that's an area of a circle as a function of its radius. You can write the area of a circle as a function of its diameter. We don't usually do that. We usually write A equals pi r squared. All right, so that's letter A. So letter B would then be to find the instantaneous, and you guys are going to get used to this word, huh? Find the instantaneous, how do you spell that? I know, right? It's a really big word, especially for a math teacher. Who doesn't? I did?
That's right.
Is it A? Instantaneous.
We're sitting on this moment.
Taneous.
Keep going.
Okay, we're going to find that instant rate of change. I'm just going to call it instant rate of change from now on. Instant rate of change of the area. Now, you know that when we did this with velocity and we found the instantaneous rate of change in velocity, all we did was take the derivative, and that's what we're going to do. Okay? So the change in area we call A prime. Change in area.
We take the derivative of the formula to find the area.
The change in area. Yes, you take the derivative to find the instantaneous change. So what is the derivative of pi r squared? 2 pi r. Ooh, do you recognize that? That's the circumference of a circle.
Can we just use all the time?
What's that?
Can we just use that all the time?
Yeah?
So we don't have to find the derivative?
Every time? No, if you know that, yeah. So the derivative of the area of a circle is its circumference. Isn't that cool? Does anyone else think that's cool?
Molly was like,
Molly, thank you, Molly. Yes, Molly. Okay, by the way, sometimes your book or maybe your calculus teacher that you'll get in college, instead of writing A prime, they might write dA dr. Okay? It's the same thing. dA dr means the change in area with respect to its radius. dr. Okay? So we're not doing this with dx or anything. It's dr because r is our variable. All right, so that's part B. Now C would then be to do like an actual problem. So we're going to evaluate the rate of change. Evaluate the rate of change of a circle when r is 5 inches. When r is 5 inches. Okay? And so once you find the rate of change, you can now find the rate of change for any radius. They just said 5, for example. So you're going to go ahead and plug it in. So A prime equals 2 pi times 5. And then make sure that you have the correct units. Okay? So this would be 10 pi, and it's the change in area over the change in radius. So what would the change in area be? Square inches per inch.
Do you want us to live in terms of pi?
Yes, leave it in terms of pi. That's beautiful. Okay, number 2. Let's do another one of these. All right, it says to A, this one's a little harder. You ready? Find the area of a equilateral triangle. Equilateral. Still don't know if I spelled that right. 2 L's, maybe. Equilateral triangle. Find the area of equilateral triangle as a function of its side. As a function of its side. Okay, that might be the hardest part of this problem. It's funny how like the calculus part, the derivative, is not the hard part, right? But finding the area of an equilateral triangle as a function of its side, that's hard. So we have an equilateral triangle here. And you could probably look this up. If you asked your phone, I bet your Siri would tell you for sure. What did you get it already?
Area is base times height over 2 for all triangles.
Base times height, Okay, so these are all the same length, right? This is an equilateral triangle. And area is base times height. Okay, but I don't have the height here, unfortunately. So it's 1/2 base times height. I have the base. The base is x. How are we going to find this height? Trig? I would do Pythagorean Theorem too. But trig would get you there too. You would do trig? How many of you guys would do trig?
Well, I guess.
You would guess, Jack? You would just guess.
I would think for half hour and then figure out what
I would probably do Pythagorean Theorem. Jack would guess. Okay, so this right here is 1/2 x. This is x, and then this is the height, which I'll label as h. And I would do Pythagorean Theorem also. Okay? So Pythagorean Theorem would be to do h squared plus 1/4 x squared. You have to square 1/2 x. So a squared plus b squared equals c squared. Okay? And let's solve for h. That's what we want. So we're going to subtract 1/4 x squared to the other side. So what's 1x squared minus 1/4 x squared? 3/4 x squared, good. And then you're supposed to take the plus and minus, but we're talking about height here, so height's going to be positive. We'll take the square root of this side, and we get rad 3 over 2x. Did you follow that? I just pretty much took the square root of everything separately. Okay, so that's the height. So now let's put it back in and find the area. Okay, so the area equals 1/2. Base, we said, was x. And the height is rad 3 over 2x. And then let's clean that up. Let's make that look nice. So the area is rad 3 over 4x squared. So that's the area of an equilateral triangle as a function of its side. Did I say to make side S? No. You can make it X, you can make it S, whatever you want. Okay, so that's the first part. That's almost harder than what we're going to do in just a second now. So now we're going to find the rate of change of this area. Yes?
Wait, so is this a formula for all equilateral?
It is. So if you ever needed it, find the rate of change.
Or is it only equilateral?
Is it what?
Is it only equilateral? Oh, we can, I'm just asking questions.
Oh, no, it's okay. You can ask questions or not. I act normal, don't I, pretty much? Or do I kind of straighten up a little bit? I act the same? Fine.
People like it. They like it when you talk in class.
It's okay. It's fine. Nothing bad happened.
I know.
Yesterday, this lady came in. This lady came in and she sat in the back, and then I was saying, we were doing complete the square, and we had to take the plus, or we had to do 1/2 b squared and add that number to both sides, and it was 9. And I'm like, you have to keep an equation equal. Like, if you had 3 girlfriends and you have 3 girlfriends, and you're going to add 9, and you're going to add 9, and the lady didn't even laugh. She was just like, I was like, maybe I shouldn't have said girlfriends. It's like, maybe apples would have been better.
You're keeping high schoolers entertained.
I know, right? I'm entertaining. Yes, yeah. And then she left, but she didn't leave. She stood by the door to listen because they all kind of erupted. I was like, stop, she's still there. It's WASP. They walked in on my devotions yesterday and sat through it. Yeah, it was weird. Okay, here we go. Find the rate of change of the area. I mean, seriously, you could really ask Siri, what is the area of an equilateral triangle in respect to its side?
I couldn't find my
I couldn't find. I don't know. But you probably could. You could probably Google it, whatever. All right, so here we go. Let's find the change in area with respect to its side. Here we go. That rad 3 over 4, that's a constant out front. You don't need to do product rule or anything. Okay, this is just a constant x squared. So bring the 2 down, and you get rad 3 over 2x.
Is the 3 not affected by the 2?
No, when you multiply 2 times rad 3 over 4, you just reduce. Yeah. Okay, so that's the change in area. And then the next question would be, you know, find the change when x is 5 or whatever. Okay, so that would be it. All right, let's do one more of these. No, we have velocity graphs to look at. You is right. All right. It says here that the volume of a spherical balloon changes with the radius. All right, so here's the volume. Yeah.
Have you ever seen?
Yeah. I have. They have them over at Party City. Yeah, they're round. They're really cool. They even have square balloons, too.
Yeah.
That might be a
Those
problem.
are bigger
You've
ones.
never seen a, I can't see it.
There's like a perfectly
One of
round
those balloons. You
sphere.
guys are gonna make fun of me. I can't use my words today. At Disneyland. Yeah.
Ooh, yeah, that's right. Yeah.
And it has the Earth one.
I know, because balloons usually aren't spheres.
They're like,
All right, so here we go. The volume of a spherical balloon changes with the radius. So the question is going to be, what rate does the volume change when r equals 2 feet? At what rate does the volume change when r equals 2 feet? That's a big balloon.
Wait, okay, why is the volume changing? Bigger?
Yeah, maybe you're blowing up the balloon.
Okay, I didn't know.
Yeah, maybe, yeah, but it's changing. Yeah, so now you have to take the derivative. See, anytime they ask for a rate of change, it's derivative. Derivative is the rate of change. So here we go. dv dr, or if you want to just write v prime, that's fine too. The change in volume over the change in radius is equal to, bring the 3 down, and you get,
Wait, do we have to do product rule?
no, 4 pi r squared. So 4/3 and pi are a constant. So anytime you have a constant, you don't need product rule. There's only one variable here, and it's r. So you bring the 3 down, you get 4 pi r squared, and then go ahead and take r equals 2 and plug it in. So dv dr at 2 is going to equal 4 pi times 2 squared. So that would be 16 pi cubic inches per inch.
How do you know what to do for that?
So when they say at r equals 2 feet, you just plug 2 in for r.
How do you know the units?
Oh, so change in volume. Volume's always cubic inches over the change in radius. Radius is inches. That really always helped me because I get confused on those a lot. Like what? Yeah. So
How come it was squared on the other one?
on what? Oh, because that was area. So area is square feet, square inches. This was volume.
always inches?
No. Oh, this was feet. Oh, shoot. Whoopsie. Woo. Sorry. Feet. I'm glad he's not here. Feet.
That's really big.
Yeah, that's beautiful.
That's a really big thing.
It is, huh? It's a huge balloon. Maybe it's a hot air balloon. I don't know. They're not spherical, though, are they? All right, here we go. Last part, velocity graphs.
Is this section long?
No, it's one problem, but it takes a little while. Are you itching to leave here? What's going on?
No, I'm running out of room on my paper.
Oh, okay.
And I'm super hungry, so I can't concentrate.
I'm super hungry, too.
I'm saying go to squeeze.
That's why you eat breakfast.
Breakfast. Okay, here we go.
That was really
Oh, shoot. Can I rewind? My son says it all the time. It just gets in my head. Okay.
Oh, I can't wait to listen to that tonight.
Dang it. All right, here we go. Suppose that this is 3 and this is -3. And I'm going to draw, this is not the motion graph. This is the velocity graph, okay? Or,
This is the last paragraph.
Yeah.
All right, so here we go. 1, 2, 3, go all the way out to 9. 4, 5, 6, 7, 8, 9. Okay. And then we're going to put some stuff in here. We're going to go, so go like this. Start at 0, go up, go back down. That should be a straight line. Looks pretty bad. And then at 4, we're going to be here to 4, 5, 6. And then at 7, so 1, 2, 3, 4, 5, 6. At 7, we're back on the x-axis. And then we go like this to 9. Okay. Here we go. I'll draw it even better. There you go. How's that? Pretty good? All right, so copy that down real quick, and then we're going to talk about it. So this is the velocity graph. This is v equals f prime of t. And t is in seconds. All right, so here are our questions. Letter A. Oh, this is number 4, I think. Number 4. Are we good? Okay, here are these questions going to be. They're very interesting. So this is velocity graph. This is not a motion graph, okay? So the question is going to be, when does the particle move forward? When does the particle move forward? Hello? We thought it was more. Whew, Chris, it's just you. Thank God. All right, when does the particle move forward? Okay, so let's talk about this. Velocity is going to be like right now. You're going to miss this.
Can you freeze?
No.
It's recorded.
Okay. All right, so here we go. When does the particle move forward? Now, some of you guys have done this before. Jack, you've done this before. So the particle is going to move forward when your velocity is positive. Okay? Velocity is positive when you're above the x-axis. Think of this. This over here, this y, these y values are velocity, right? This is v of t over here, and this is t. So this axis is v of t. The x-axis is seconds. So when does the particle move forward? Kevin said it. First 3 seconds. From 0 to 3. That's when it moves forward. It's weird because you're not looking at this as, oh, I'm going up and I'm going down. Okay? This is a velocity graph. The velocity here is at 1, it's maybe 1. And then it's 2, and then it's 3, and then it's all the way to here. And then the velocity is negative. So when velocity is positive, that's when the particle is moving forward. Question B. When does it move backward? Yeah, when it's negative, right. When v of t is negative. So I want to look at the negative values. The negative values are when it drops below the x-axis. So that happens from 3 to 6, 7. 3 to 7. Perfect. Okay?
Can you do acceleration graphs too?
Yes, we're going to do that.
This one or no?
Yeah.
Oh, it's easy.
Yeah. Okay, then letter C is going to ask, when does this velocity, or when does this particle stand still? It stands still, yeah, when the velocity is 0. Perfect. 7 to 9. So it stands still from 7 to 9 because velocity is 0 there. The height's not 0. This is not a height graph. You have to keep reminding yourself of that because that's what you've seen your whole life. And all of a sudden now it's velocity with respect to time. All right, question D. Let me go over here so I can. Question D. When does this particle speed up? When does the particle speed up?
1 through 5, 1 through and.
Yeah.
67.
Yeah? It speeds up from 0 to 2, right? Did you get that? 0 to 2. Okay, it speeds up. It's going faster. Velocity is going faster. It's increasing. And then it also speeds up from where? 6 to 7. Ooh, yeah, 6 to 7. Six to 7. Yeah, it's speeding up as it goes into negative too.
Yeah, that's what I was thinking.
Yeah, from 3 to 4, right? From 3 to 4 also. I was just thinking that too.
2 to 4? Does it start at 2 and goes down to 4?
Well, it's going backwards.
We have to go.
Oh. Okay, so right here, the velocity,
I care what happens.
it wouldn't be 2 to 4. Let me show you why. See, this velocity is 3, and then it's 2, and it's going down. It's slowing down. Then it hits 0, and then it starts to pick back up in a backwards direction. You guys are leaving?
Yeah, we have to be. I told you, we're in trouble.
Okay.
Like legit?
No.
Trevor,
Not allowed to talk about it.
Okay, last question.
Good job.
When is the velocity equal to 0? When does the velocity equal 0? It equals 0 at 0, also at 3, right? Velocity is 0, at 3, and then from 7 to 9. Velocity is 0. Okay, so take a look at this. If you were looking at this graph, this guy, he's starting at 0, right? He's getting in his car or whatever, or walking. Let's say he's walking. He's picking up speed. He gets to a really high speed of 3, and then he starts to slow it down, and then he stops. He stops in his tracks. He stops right there. And then he walks the other direction. He walks negative or backwards or whatever. And then he's picking up speed, and then he's going the same rate for a while. And then he's slowing down to 0. And he just stands still. Okay? All right. Now, they are going to ask you for acceleration. Okay? I'm not going to ask you for the acceleration graph, but I am going to ask you, letter F, when is the acceleration positive, negative, or 0? Okay? Now, think about this. Acceleration is the derivative of velocity, right? Acceleration is the derivative of velocity. The derivative is rate of change. So where I'm looking at acceleration being positive, that's when my slope is positive, right? So where do I get a positive slope on this graph? From 0 to 2. I'm just going to write it like that. 0 to 2. Where do I get a negative slope? From 2 to 4? 2 to 4. Okay. Oh, I also get a positive slope from 6 to 7. So let's go back to positive. Acceleration's positive also from 6 to 7. Okay, and then where is it constant? Where is it 0? 0 slope would be from 7 to 9. And that's it. Yes, thank you, Trevor. Trevor also said that it has a constant slope of 0 from 4 to 7. No, 4 to 6.
Oh, sorry.
No, but you were right. Really good.